are going to go through our problem set solutions. So let's look at this scenario of a cantilever beam. So PVC, so I'm going to go ahead and put this on the side screen right here so that we can see and solve at the same time. PVC beam, so we know that our Young's modulus is going to be, let's just make sure that I quit my kernel, because I might have been working in basically in another notebook previously. So my Young's modulus, on blue, 1 times 10 to the 9, so gigapascal. Poisson's ratio for polymers 0.4 approximately. We see our applied load is equal to 1 kilonewton, so 1 times 10 to the 3 newtons. We see that we have the length of our beam is equal to 50 meters. The thickness, which is essentially going to be our height, is going to be 20 inches, so 20 times 0.254. Our base is going to be equal to 3 feet, so 3 times 12 times 0.0254. And I'm pretty sure that's about it. So the strain gauges are placed 0.1 meters from the cantilever beam support. So basically from here to here, this is 0.1 meters. So we know that our D, so we need our actually bending strain equation. So EB, our bending strain, is just going to be 6 times P times D divided by Y divided by Y times B times H squared. So that's our bending strain. So our D is our distance from where the load is applied, which is we are applying the load halfway along the length of our beam. So our D is going to be equal to our length divided by 2 minus 0.1 meters. So that's it. So the distance from where the load is applied to basically that distance there. So that's pretty much it. So 0.1 meters from the cantilever beam support. There it is. So let's go ahead and let's go subtract, or actually we got that. So we've got our EB, so our bending strain, because we have all of these parameters in here. What else are we told in this problem? Excitation voltage, so VI is equal to 2 volts. When the load is applied, our DAC read 1 volt, so delta V naught equals 1. And let's scroll down here. All right, so what assumption must be made to solve this problem? So we're assuming that all the gauges have the same resistance, because that's how we could say that the delta V naught is equal to 1. Write out the strain in each strain gauge. Well, we know that our strain in my 2 is going to be equal to E bend plus ET. My strain in the 3 is equal to negative E bend plus ET, where my thermal strain is equal to alpha delta T. My strain in the 1 direction is going to be compressed, so it's going to be plus nu EB plus ET, and my strain in the 4 gauge is going to be equal to, so we're pulling minus nu EB plus ET. So let's go ahead and define that all nice and clear right here. So let's write those down. So my strain in the 1 is going to be nu times EB plus ET. I'm going to say also my ET is equal to alpha times delta T. Let's define those right there. So I've got that. My E2 is equal to EB plus ET. My E3 is equal to minus EB plus ET. And my E4 is equal to minus nu times EB plus ET. So there we go. So let's go ahead and continue. So wrote out the strain gauge. What is the gauge factor? So we know that we're going to use the following equation. So not divided by I equals F divided by 4 times epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4. So we will go ahead and write that down there. So let's do E1 minus E2 minus E3 plus E4. Oops, not ER, E4. That's going to give me 0. So for this configuration, I'm not going to measure anything here. So it's a kind of a null problem. So let's go ahead and so let's solve the last problem, but we remove 3 and 4. So what is the gauge factor now? So gauge factor previously, we couldn't even solve for it. So now let's solve for delta V naught divided by VI equals F divided by 4 times, now we're removing 3 and 4, so E1 minus E2. So let's solve for F. And there we go. That's our gauge factor. Negative, it's weird, but again, it kind of solves the problem. Now, for the last experiment, the temperature was increased by 50 K. And then it's asking us, what is the thermal expansion coefficient of the material? Well, we can't solve for that value because our ET cancels out. Now, if I just use gauge 4, now I can solve for that value. So we're saying that delta T is equal to 50. So 50 right there. And now I want to solve, and we said that our F was equal to, this was our gauge factor. So let's assume that it's the same for this problem. So we solve for our gauge factor. So I want to solve for basically delta V naught divided by VI set equal to F divided by 4 times just E4. So I want to solve for my alpha. And I solve for my alpha, and this is the value that I get. So, and remember that's units of inverse K. So that's the first problem done. So let's move to the second one. Working with a titanium alloy now. So I'm going to go ahead and quit this kernel. Look over here. So now let's go ahead here. So I'm going to do number 2. So working with a titanium alloy that will be used to replace arteries a la the Terminator. So titanium, so my Y is equal to 100 times 10 to the 9. My nu is equal to 0.4. 0.3, excuse me. So here we go. Dimensions of the arteries have a 100 micrometer thickness. So my T is equal to 100 times 10 to the minus 6. And, thickness of 3 micrometers, And then I have a diameter of 100 micrometers. So my radius is equal to 50 times 10 to the minus 6. So let's check if I'm a thin-walled pressure vessel, because I have radius and thickness. There we go. That is greater than 10. So now I can move on to, I know that my sig H equals del P times R divided by T. Sig L is equal to sig H divided by 2. I know that my EH is going to be equal to these values as well. So let's go ahead and let's kind of figure out some of these values. So titanium will typically fail when we reach 30% strain. I place a shunt resistor, so I have a shunt resistor across arm 2, Wheatstone bridge. All gauges have a resistance of 120 ohms. So my radius, or my resistance, is 120 ohms. And then my, basically my shunt resistor is, my RS is equal to 100 kilo ohms. So when the switch is closed, my DAC reads 5 volts, and the gauge factor F is equal to 3.8. So I close my switch. So I need to look at, so my F is equal to 3.8. My resistance is equal to 120 ohms. My RS is equal to 100K. So 100 times 10 to the 3. So now my equivalent resistance, when I close the switch, or equivalent strain, not resistance, EQ strain is going to be equal to my absolute value of minus 1 divided by F times my R divided by R plus RS. There we go. So that's my equivalent strain. And so that's the strain I get when my DAC reads 5 volts. So now let's go ahead, let's write out the strain in each of the strain gauge. So I am, let's see, my strain in my 2 is going to be measure essentially the strain in the 1-1. That's the thermal strain, and I know that my strain in the 1-1 is going to be equal to my hoop. My strain in the 2-2 is going to be equal to my longitudinal. So my 4 is equal to strain in the 2-2 plus strain, thermal strain. So strain in 2, strain in 4. So that's the strain in each of the strain gauge. What's the amount of pressure that these synthetic arteries can withstand? So we were told essentially that we're going to fracture at 30% strain. So we know that that corresponds to our hoop strain, which is equal to 1 over E times sig H minus nu sig L. So I need to solve for that pressure. So I need to solve, because when my hoop strain, hoop strain is always larger than my longitudinal, when that reaches 30%, so 0.3 is equal to 1 divided by Y times sig H minus nu times sig L. So I need to solve for my del P, because that's the only thing remaining. So this is my del P. So this is my delta pressure. So my del P equals this. So we've got that value here. So my sig H equals this, my sig L equals this, my EH is this, my EL is equal to this. Oops, let me write out. EH equals basically 1 divided by Y sig H minus nu times sig L. And then my EL is equal to, makes sense, sig L minus nu times sig H. And there we go. EH, EL, all right, we are getting there. We're getting close. So We've written out the strain in each strain gauge. What is the maximum amount of pressure that these synthetic can withstand? We figure out the delta P. Right before fracture, what will my DAC read? So this is an important point. So we figured out our equivalent strain. When we close the switch, our DAC measured this 5 volts. And now we know what our total strain is going to be the following. Total strain is equal to minus E2 plus E4. So I need to solve for what's the voltage at this total strain here. So if we remember kind of our equation, our total strain, we're calling this V2. I'm going to call this my V1. So this is my V1. My total strain is going to be equal to my equivalent strain times V2 divided by V1. So that's kind of our equation. So let's go ahead and let's set this equation up. So my total strain, which is going to be equal to, so minus E2 plus, actually let's go ahead. E2 is equal to, let's go ahead and move up here. E2 is equal to my EH plus ET. My E4 is equal to my, even though it's on the back, it is equal to my EL plus ET. So when I do that, I have to now, I will go ahead and grab my total strain. Let's go back over here. So my total strain is minus E2, so I need to solve when minus E2 plus E4 equals my strain equivalent, EQ strain, times my value that I don't know, divided by VI, which was 5 volts, I believe. So my V1, 5 volts. Then let's solve for X. So that will be my, essentially, my voltage value when we kind of compress this. So there it is. Excellent. That's right before that's what my DAC's going to read. So look at the stress state below, and note the bending will push the sheet out of the page. Write the full expression for the strain measured by each of the strain gauges. So we're going to go ahead and look at E1. So we have some bending that's going to pop us out of the board. We have some strain in the 2-2 direction. So in 1, we are going to measure essentially positive bending plus thermal plus my strain in the 2. My strain in the 2 direction is going to be equal to my strain in the 2 strain gauge is going to be equal to my thermal, and then when I pull that out, it's going to be minus nu EB because it's going to compress those wires, and then I'm going to have the strain 1-1. The strain in the 3 is going to be equal to minus E bending plus E thermal, and then plus the strain in the 2-2. And then the strain in the 4 is going to be strain in the 1-1 plus thermal, and then when it's in the back, it's going to be plus nu E for bending. There we go. Now, let's get to kind of our final problem. So I have placed a delta strain rosette on this material, and I've obtained strain in the arms. So I have, let me kind of close out everything here. Let's close out this. So I have EA. EA is equal to 183 times 10 to the minus 6. Oops, 10 to the minus 6. EB is equal to 60 times 10 to the minus 6. And then my EC is equal to 10 times 10 to the minus 6. So I am going to write out the principal stress, stress and strain states and rotation to get these states. So I know I'm going to have to solve a series of equations simultaneously. So I need to solve when basically I'm going to choose my reference as my EA. So I'm going to have to choose this is equal to C plus R times cosine of 2 times, cosine of 2 times theta. And then I'll use that. And then I'm going to also do the same values here. So let's go ahead and solve these out. So here, 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 go. So if I'm choosing EA as my reference, so this is what type of rosette? It's a delta rosette. So our delta rosette will be a rotation of, I need to make sure I'm in degree mode. So degree. So for my B, I'm going to rotate counterclockwise 60 degrees. So that is going to be 2 theta plus 120 degree. And then for C, it's going to be 2 theta plus 240. So there's my answer. Go here, solve for theta, C, my R, theta. So when I do that, let's get us EB, EA, EB, EC, So let's see, where does it not like our solutions here? I'll tell you why, because we're not in degree mode. And that's why we need to be careful. So let's go ahead and look at this. So because I chose A, so I'm going to take the center plus my radius, so I'm taking this angle. So my center is going to be this. My theta, or my R, is going to be this, the positive value. So I want the, and then this is my theta angle. So my theta is going to be equal to this. So this is my theta equals this. So CR, CR and theta. So my principal strain is going to be, so this is the rotation that I need to get to my principal stress state. So this degree, E1 is going to be equal to C plus R. E2 is going to be equal to C minus R. And then I'm going to choose that my material is not stated in this problem. There's a little bit of a typo. But I know that the equation to get to my principal stress state is just going to be sigma 1 is going to be equal to sigma 1 minus sigma 2. And then sigma 2 is equal to 1 over E times sigma 2 minus mu sigma 1. So I'm going to solve those equations. Oops. Oh, excuse me. Sorry about that. That is a little bit of typo. Not a little bit of a typo. It's a major typo. You can't solve the same values. So excuse me. That's why you don't work too fast with these problems. My strain, my principal strain in the one direction is going to be this. Sigma 1 minus nu sigma 2. And then my strain, principal strain 2 is going to be equal to 1 over E sigma 1 minus nu sigma 1. So we can solve those values once we have those values here. So I'm going to solve this problem pretty much exactly the same way. So I'm going to clear out this kernel right now. And this next one, now we're dealing with a problem, again, still delta rosette. And so I see the strains in A, B, and C respectively. So I'm going to go ahead and just keep a lot of this because the rotations are going to be exactly the same. So now I have 12, I have 58, and I have 170. But now you can see that my EA, I want to choose essentially the negative, radius here. So I'm going to choose this angle as well. So my center is now here. My radius is going to be here. Choose the negative radius, but anyways. Actually, I should choose the negative radius in my solutions, or at least the negative angle there. So we want that radius to be, C plus R. Again, we could just kind of write out those values here. So right here, and then my angle. So I'm not in my principal stress state, so my angle is going to be the following right here. And let's get this guy. So that's my, that's my theta, that's my R. Here's my new E1, here's my new E2, and there we go. We're almost done. But now I placed a new proprietary strain gauge that has 3 arms, A, B, and C. So we had our delta rosette. So basically here, here, here. So A, B, and C. So I have a new rosette that's basically, I have between, basically, sorry, this is A and B, and this is B and C. So it has a 23 angle between A and B, 33 angle between B and C, and the A arm is placed from the, so the new A arm, so this A prime, is 15 degrees. And then the new arm here is 23 degrees, and then for B prime, and then the new arm here, the C prime, is this angle here is going to be 33 degrees. So if I want to find the new AA prime, I'm going to do the following. So I'm going to do EA prime is going to be equal to C plus R times cosine of 2 times theta plus, what's the angle here? 30, right? Because again, I'm doing that in rotation essentially here. So that angle is going to be 2 times 15, so 30, and I'm going to keep all of this in my degree mode. So I'm just going to keep this actually as, let's write this more general, 2 times 15. So, and then I'm going to keep everything in degree. Let's kind of blow it up now. Actually, I'm going to have to close it in just a second. So that's my new EA prime. All right. What about my EB prime? Well, that's just going to be EB prime. What's the difference now? So again, I'm still using my reference because in the first part of the problem, I chose A as my reference arm. So what's the angle between our old A and our new B prime? Well, that's just going to be 2 times 15. 2 times 15 now plus 23. There's my new EB prime. And then now, finally, so 2 theta, and let's get these values essentially here. So again, it just depends on essentially where you are working with in this kind of problem, and where we're essentially how we're defining essentially our, actually we need our basically our negative r value, but we'll get that in just a second. So we want that r value here, and then our EC prime. So we just want that angle here, because if we choose this angle, so c plus r times cosine of 2 times cosine of 2 times theta. Let's make sure we still get our. Actually, sorry about this. Actually, we need to do this. So actually, we want, oops, c minus r times cosine of 2 times theta in degree mode. Sorry about this. Degree. So now we get this value. So actually, we need here, excuse me, for our EAs. These are still fine for our E1s and E2s, but we're just going to kind of make this a negative r, because again, we chose this value here. So for E1s and E2s, but for once we're kind of getting into our EA prime and B prime, we need to make sure we kind of keep those values consistent. You see that these will just basically flip. So we still have E2 is actually greater than E1, but anyways, it's just kind of this negative value here, because again, we're choosing as a reference EA, so we're going to have to subtract essentially from R to get that value. But anyways, so let me kind of just redo this here, do this one here, and now our EC prime is just going to be the same expression. But now, as we can see here, we are rotating an additional 33. So 15 plus 23 plus 33. So 15 plus 23 plus 33, and there we go. That's essentially the answer that we're going to grab there. So just kind of a quick notification again. So if we were asked in that previous problem to look at like the new theta values, we have to include that negative r. But you see your E1 and E2, it just depends on, again, if you want the absolute value of the r to calculate E1 and E2, you're going to get still the answers are going to kind of lead to the same values. So we want the absolute value of r when we kind of look at this equation. Again, you would kind of know that again if you're when you're actually doing it on your Morse circle. So E2, E1, so those are consistent, but now this is going to give us the kind of correct values essentially due to the circular symmetry. But again, the approach is what we're kind of looking for here. So that's pretty much it. So do well on your exam 3, and I will, oops, I don't want to record mine. Do well on exam 3, and I will see you all a little bit later next time. Thanks. Bye.